Good afternoon, everyone. My name is Jacob Johnston. I'm a co-founder and the head of supply chain at Foundation Devices. Today in this workshop, I'm going to be talking to you about device manufacturing in the Bitcoin space, specifically hardware wallets, nodes, and Bitcoin miners. My company, Foundation, we actually make hardware wallets, Bitcoin hardware wallets in the United States. And our mission statement is to basically design and manufacture Bitcoin-centric tools that empower you to reclaim your sovereignty. So last year, I was had the pleasure of speaking at the hackathon about Foundation, but today I'm excited to talk a little bit more about the manufacturing side of things and actually what goes into making these devices and getting them shipped to customers all over the world. But first, I kind of wanted to go over the main types of hardware in the Bitcoin space that exist right now. There's some other stuff. And also in this presentation, I'm not going to get into too much minute detail, but kind of just going to take things at a high level overview. But yeah, there are other hardware devices in the space, but these are kind of the big three. So for hardware wallets, of course, you have Foundation, Passport, and then there's some other options, Trezor, Ledger, Cold Card, etc. We actually use a lot of our open source code from a couple of these, Trezor and Cold Card, and then also contribute back and add on to that code space. And Ledger is more of a closed source option, but they're probably the one that everyone's most familiar with. They're the little USB stick that has the small screen and the two little buttons, and they've been in business for the longest amount of time. There's also nodes, which are basically home servers, and a lot of these are what you would call like a DIY type of product, where you would buy all of the materials, get them shipped to you, and then put everything together so you can kind of verify all the components and build it yourself. You can also do that with hardware wallets. So there's a couple cool tutorials online that'll walk you through how to make your own hardware wallet and how to secure your own password without the need of a manufacturer. And then another one that people are broadly familiar with because it can make you money is the mining hardware side of things. So the miners. And some people also refer to these as ASICs, which are application-specific integrated circuits. Those are the chips that actually go into the mining hardware. And yeah, there's a lot of big players in this space as well for the miners. There's WhatsMiner and Bitmain, which are two big Chinese companies. Bitmain probably being the leader of all the mining companies at the moment, and they have been for a long time. They also run a pool, a mining pool, which we can talk more about later. But Canaan is another option, which makes Avalon miners. And then also Intel most recently announced that they are potentially getting into the Bitcoin mining space. So that'll be exciting to see. There's some preliminary specs and some talk of them giving chips to other companies to build miners. So it'll be awesome to see their entry into this space and see if that gets more people into Bitcoin or into Bitcoin mining. So what is a hardware wallet? If for those of you who don't know, it's basically just a device that stores your Bitcoin private key, which is your password to your Bitcoin. There's a lot of benefits of having a hardware wallet, namely the security. So whenever we're talking about Bitcoin private key storage or key storage in general, there's what we call hot storage and then cold storage. Hot storage would be storing your private key or password on something like your laptop that's internet connected, or with a service that, like a website that's a custodian for your Bitcoin that helps you, gives you software to track your Bitcoin holdings or to transact with Bitcoin. Hardware wallets are namely not internet connected. Most of them, if not all of them, are not internet connected. There might be some Chinese hardware wallet knockoff that has internet, but most of the time they're not even physically connected, or at least for our device, for Passport, it's not physically connected. It uses a camera to communicate through QR codes. So you're kind of taking away that attack vector of being connected to the internet or being connected to a service that could be compromised or hacked into, and you're taking control of your password and putting it in your own hands. The passwords or private keys are also stored in a protected area on the device called a secure element. These chips are used in tons of different things, even in iPhones, to store different keys. And so, yeah, even the device being offline, we kind of take it a step further and also ensure that someone can open up the device and get into the chip and take it off of the chip or off of the device and use that somehow maliciously without even needing access to actually using your device. So you can also easily sign transactions with hardware wallets in conjunction with nodes or by themselves with partially signed Bitcoin transactions, which we'll get into later. But the bottom line here is that you're really going to improve your security by using a hardware wallet. You're going to improve your privacy, and you'll also get some utility out of it because they're small and portable. You can carry it around. And yeah, there's a lot more to this, but this is just kind of the high level overview that I wanted to make sure everyone was kind of caught up on. So in terms of all of the available hardware wallets, we felt that they really needed an upgrade. So we made Passport, which was our first hardware device that we had launched. We built 1,000 of these Founders Edition Passports and sold out of them pretty quickly. So now we're going on to make another iteration of Passport that will be shipping next month. So we're really excited about that. There's a lot of changes and we implemented a lot of user feedback. So be on the lookout on our website or on our Twitter for more updates around all that stuff. So now onto the mining side, and this is where we could get really granular and specific, or we could just be really broad about it. So I'll try and meet somewhere in the middle. So mining is the process of using computer hardware and energy to circulate new Bitcoins. It's also critical to securing transactions or confirming transactions. And these transactions, with Bitcoin, they need a certain amount of these confirmations before they can get validated and added to the blockchain. So without miners, there would be no blockchain. It's quite literally the backbone of everything that's going on. So as I mentioned earlier, mining hardware uses ASICs, which are these application-specific integrated circuits. And ASICs are only used for one specific thing, for one algorithm or for one computational set of problems or for a specific use case. So these ASICs, like I just said, solve computational math problems to be able to basically race for the next block. And for those of you who don't know what a block is basically just a grouping of transactions. So as you can see, from the screenshot on the right-hand side, this is a block on it from a block explorer. So this is just showing you all the information of the block. It shows you that there's 1,768 transactions included in this block. So these miners, what they're basically doing is they're grouping together all of these ASICs, all of these chips, to be able to have enough computational power to what we call get to a target hash. So there's kind of like a target hash that the network displays for a block and gives to the miners. And then the miner has to use their computational power, what we call hash rate, to generate a bunch of what we call nonces. Nonces are numbers that are only used once, basically, and they're basically just guesses in order to get to that target hash. And so the first miner that generates a nonce with their computing hardware or with their computer hardware with their miner that is less than or equal to the target hash discovers the next block and gets rewarded with what we call block reward, which is very significant, 6.25 Bitcoin. In order to have enough computational power, though, to be able to guess or generate enough nonces to get to that target hash, you have to have a lot of mining power. You have to have a lot of hash rate. So that's why you see typically these big, mining farms, industrial warehouses that have tons of different ASICs in them that are just, blaring like jet engines basically in there because they need a lot of them to be able to ensure that they have a chance or a higher probability of hitting that next block and getting that block reward. And so earlier when I mentioned mining pools are basically ways that you can ensure that you have a higher chance of getting a chunk of that 6.25 block reward every block or some blocks. And so people will group together and they'll put all of their miners on basically the same, what we call pool. And then that pool kind of works together to generate enough guesses to be able to average out and get more blocks than you would block rewards than you would alone. There are solo miners that exist, but it's very difficult to, or rather the probability is very low that you will and be the singular person that hits that next block and gets that block reward. As you can see from the screenshot, though, the block reward says 12.5 Bitcoin instead of 6.25. And the reasoning for that is every 4 years, there's something called the halvening. So this block reward will actually go to 3.1257, whatever it is, half of 6.25, and after 4 years from it changing from 12.5 to 6.25, which I believe was just recently in 2020 or 2021. So yeah, 4 years from then, and it'll go down even more. And also, real quick, there's also something called difficulty, which is basically the hardness or the difficulty of the target hash. So over time, it actually gets more difficult for these computers to generate significant guesses to be able to hit that target hash. So it's kind of following along right now with Moore's law a little bit, but as long as computational power gets better and better, and we get better semiconductors, and we get to the point where they're continually keeping up with it, then we should be fine. But the difficulty gets adjusted based on how many miners are on the network and generating nonces for transactions, and also how many transactions are occurring on the network. So the difficulty is a little bit of a complicated thing. I guess the target hash and the nonces might be as well. But yeah, again, if anyone wants to talk more about mining or learn more about this, I encourage you to reach out, or go online. There's tons of YouTube tutorials and information that people post about all this, because Bitcoin is a big open source community, and people love to talk about it. People love to teach other people, and it is really invaluable to know all of this, to really understand what's going on behind the scenes. So yeah, this is kind of what I was talking about. Like this is what you would typically see on the news, or some Business Insider article talking about how Bitcoin consumes too much energy or something. But yeah, this is not the average scenario for Bitcoin mining. There are people that run shipping containers or run a couple of miners in their house, but this is really where the people who are running pools or hosting other people's miners, this is what that looks like from like a more industrial perspective. And then these are kind of the evolution of how ASICs or Bitcoin miners have evolved. So up here on the top left, this is a miner that came from a company called Butterfly Labs that was actually riddled with like delays, and really early on miner. I believe it was 2012 or 2013, maybe even 2011 that they started. And as you can see, those two big copper plates in the picture, those are where the chips are basically on that, and those big things on top of them are heat sinks that are pulling out heat from the chip, because it was all very new then, and people were still kind of trying to figure out what the best method of generating the most nonces was, and how could we fit the most ASICs on the board. And I believe that this one only had 2 chips, but they were a special type of chip that was designed, that they designed for this. But then we get to these kind of brick designs, as you can see, and then even stacking the bricks nowadays with the power supply to the side, and then a control unit on the top. So that's kind of typically the configuration. Is the reason why they build these like tunnels is so that the heat can easily be sucked in really quickly, and then be pushed out really quickly as well, so that there's an even transfer of heat while the computer is running 24/7, because these never get unplugged. So unless they have to for maintenance or for some other reason, because they're generating revenue. So the longer that they're online, the more use you're going to get out of them, the more revenue you're going to generate from them. And so you can see that they're kind of getting to this form factor of trying to maximize efficiency, minimize heat, and it's a big game of trying to balance all of that, and also make it out of materials that are long lasting and durable, and make it in form factors that can configure in those industrial settings to make sure that there's enough space, et cetera. And so now, after these configurations, there's been a lot of talk around what we call immersion cooling. So this picture on the right, you actually see all of the miners are dunked under liquid, and they're using a special type of two-phase oil in this setup that's really good at pulling all of the heat out of the chips and out of the miners, and then pushing it to the top. And then recycling that material below it and continually doing that process over and over. So that's a very, very cool thing. You get a lot more efficiency out of it. And it's just now really starting to kind of gain attention and, research and development, et cetera. So I think that's probably, where we're headed in terms of these larger Bitcoin mine style setups, or even at home setups. I've seen people use immersion liquid and have good success. So really interesting stuff, and it'll be awesome to see where we go from here in terms of the overall industrial design and direction of the Bitcoin miner. And then this is kind of just an explanation of the ASICs themselves. So each of these rectangle little squares here actually are ASICs. And so in one of these miners that you saw on the previous slide, you would typically probably find nowadays hundreds of these chips inside. So they come in all different shapes and all different packaging types, is what we call these. The black material you see around the chip is a package. So there's different methods and types of packaging that you can use to actually attain different goals, like whenever you're putting it down onto your printed circuit board. So most of them are what we call flip chips, but then there's also different styles that they can use to get different things out of them. And yeah, so that kind of covers overview wise the Bitcoin mining side of things. And so now I guess we could transition to nodes. So nodes are basically any computer that run a Bitcoin implementation and stores the blockchain. So like we were talking about with miners, whenever they provide transactions with confirmations and they push those to the blockchain, nodes can then validate that history of the blockchain and be able to easily broadcast transactions to the network, because they have the entire history right there at the node's fingertips. So nodes share information with each other to keep each other up to date on the current state of the blockchain, so that they know which transactions are valid and which transactions to throw out, and which chain is the most valid chain. So you can this peer-to-peer sharing between the nodes happens over the internet usually, but you can also use satellite networks, mesh networks. You can even use radio frequencies to do this. So tens of thousands of nodes exist, and there's not really a big need to add a node to what we call bolster the network, but it's always good to, because just in case some percentages of nodes go offline, there's backup nodes that can easily take their place. But yeah, the benefits are really, again, similar to owning your own hardware wallet and custodying your own funds. Nodes allow you to create and broadcast transactions on your own. You get the full history of the blockchain to be able to compare against. You avoid compromising your personal information, with an online service. And then you can also create partially signed transactions on nodes, and then you can sign them offline with your hardware wallet that's not connected to the internet. So you're keeping your private key, offline with the hardware wallet. You can set up the transaction with all the information on your node, and then you can use your hardware wallet to actually complete that transaction, and then your node can broadcast it. So your password never touches the internet in that scenario. And then like I was saying, with storing the entire blockchain, it lets you enforce the honesty yourself. You don't have to rely on someone giving you that information. It's pulling it directly from the Bitcoin network and giving it to you on your node. So it's a good way to eliminate the need for trust. And so these are what a lot of the different nodes look like. Like I mentioned, they're pretty DIY. So up in the top left, you can see I believe that's a Raspberry Pi. And then they have like a little LCD that they've attached to it, and then obviously connected it to power. There's a couple of other options. A popular option is the Bitcoin machine, which I believe is made by Umbrel, and then there's a couple of other like MyNode and the Start9 Embassy that's just recently came out. So really exciting to see that there's so many players in this space, because nodes are very important for Bitcoin. So yeah, I think that we'll probably see a lot more of these hit the market in the future. So yeah, this is kind of what I wanted to talk about mainly for the talk. So I'm glad that I got the chance to give like an overview of the three main things that I believe are the big pieces of hardware in the Bitcoin space. But now I want to talk about how you actually design and manufacture a piece of hardware for the Bitcoin space, or even, not for the Bitcoin space. A lot of this can be applied outside of the space and into other products and manufacturing in tons of different industries. So the top line kind of just describes, if you were going to make a miner, right, you obviously have to design the ASIC, and then you have to go manufacture it. Obviously, there's a lot of different things that are involved in those two steps, but this is kind of just the overview of, you design the chip, you get it manufactured, and then you have to have it packaged, like I was talking about, where you have it in a concise form factor where a machine can pick that up and place it onto a board, and that all the electrical insides are protected with that packaging. After they get packaged, then you have to test them. And during the testing phase, they do something called binning, where they'll test the performance of a certain number of chips, and they'll put it into different ranges. Like this is 80 to 100% of the best performing chips. This is 60 to 80%, et cetera, all the way down, so that they have an idea of, well, what percentage of their chips are in what range, and then they can kind of maybe design different products off of different performance chips, or make sure that at least the same chips with the same performance are together to prevent some form of electrical issue. And then once you get to the spot where you actually have an ASIC, which is getting through that is the hardest part, then you move to designing the printed circuit board. And there's a bunch of different steps that are involved in the printed circuit board as well. And I actually have a slide later where I'm going to talk a little bit more about the actual printed circuit board. But in terms of assembly, after you have the printed circuit board, there's also a bunch of steps at the factory that board has to go through before it's able to be put into a product. So you can see all of those there. I won't go through all of them, but if someone has specific questions about any of those, please reach out or let me know. And then for industrial design, you also have all of the plastics, all of the metal, any other materials, like if you have magnets or foam or screws, stickers, and everything else that goes into the product other than the printed circuit board, you have to design all of that. So typically, when we want to design a product, we kind of think about, what's our inspiration for this? Why are we doing this? What do we want it to look like? What colors do we want to use? How do we want it to feel in your hands when you're using it, et cetera? And that kind of, all of those things kind of guide the decision-making process for whenever we start to get the general form factor for the product figured out. And then we'll go and prototype it and evaluate those prototypes, and keep doing that over and over again until we're happy with where we're at, and we think that it's in a position to be reviewed for manufacturing. So you kind of design what you want, and then now it's time to figure out, well, is what we want manufacturable? If not, how do we resolve that? How do we fix those problems? And if so, great, let's move forward. So you go through a lot of those evaluation stages until you get to tooling. And then whenever you want to tool your parts, there's even more sampling, more evaluation to dial in that tool that's producing your parts for you, to make sure that over time you're getting repeatability of exactly what you want out of that tool. And then when you get the parts back, you also have to inspect them, and then you can finally move into production after that. And then when you receive the parts, there's also an inspection period at the factory to make sure that what you were evaluating and doing during your T1 and T2 parts, everything is still the same, and everything's being quality controlled and ready, set to go for production. And then once you have all of your printed circuit boards, you have all your plastics, you have all your metal, you have everything else you need. You're going to move into assembly. So that involves integrating all of that stuff together. And there's a lot of involved processes that go into doing that, such as, you have to figure out how much time it's going to take, figure out which steps are first, figure out what the best way to put everything together is, how to save time. Maybe that involves creating a fixture or a jig to hold something so that someone doesn't have to hold it a certain way every single time. And you kind of just dial all of that in as you scale and as you build more and more of the same thing. But it's very important at the beginning to have a strategy and to think, well, if we do this, it might take a long time, but if we do this, we could save, 10 to 20 seconds per unit, and across tens of thousands of units, that can really make a difference. So after everything gets integrated, then obviously you test it. And so, testing goes all throughout the process, whether you're in, the chip testing, or you're testing your printed circuit board, or you're testing something that goes into the integration, or you're testing the entire device integration itself. It's always important to be testing as much as you can, where needed, all throughout the process. And then after everything's integrated and tested, you can package it up and ship it. So let's get a little bit into some more details here. And I'll show you a bunch of cool pictures. So yeah, prototyping is all about prototyping. You got to really iterate as much as you can. So generally, whenever we start out, we try and start with something that's like a very rough form factor of what we want. Kind of get an idea for its weight, how it feels, overall typical look and design, and then we kind of start dialing that in with different features. So as you can see, to the left, we started with just a basic aluminum CNC cutout of what we thought Passport was going to look like. And then we anodized it. Maybe we want it to be black instead of silver, or maybe we want it to be black instead of white. And then we also added kind of like a plastic thing where the screen would be, just to see the contrast and how it would look. And then we moved to 3D printing and start 3D printing different prototypes for everything, and figuring out, well, how many parts are we going to have, where are things going to separate, and how is all of that going to fit together. And then, kind of using those, we can start to design packaging and kind of get a feel for, well, do we want the box to look like a pizza box like this picture shows, where it's flat and it flips up, or do we want it to be a setup box like an Apple iPhone where you pull the top off of it, or do we want something different, etc. You kind of just have to try as many different things as you can and get an idea for exactly what you're trying to go for, and make sure it fits your needs and your wants exactly how you want it. And so this will kind of give you an idea for printed circuit boards. Obviously we prototype them, but how are they made specifically, you might be wondering. Well, printed circuit boards are where all the electronic components go onto. So anything that needs to be connected to the power, it'll have a connector on the printed circuit board, or anything that like accessories like a micro SD card, or all your capacitors, all your resistors, the memory, et cetera, et cetera. It all lives on this printed circuit board. So generally, printed circuit boards are made with a process called photolithography, which is a pretty complicated process and involves like some chemicals and UV curing and washing and et cetera. But from a basic standpoint, printed circuit boards are just made from fiberglass or glass reinforced plastics that are covered or sandwiched by copper. And then they have a series of processes where they print, the traces, or the locators of everything, where everything's going to go. And then they use the UV to cure on top and etch into the copper traces, so that all the electronic components, whenever they get placed, will be connected. So it's a lot more complicated than the way that I just explained it. But I tried to just give a basic overview. I've actually toured a printed circuit board facility before, where they're have all the machines moving tons of big panels and dunking them in chemicals, and and then the process where they squeeze everything together and print on top of them. And it was all, even though I've walked through it and I've seen every step of the process, it's all a lot to take in and very involved. So we're really lucky, in the manufacturing business, you have to have partners that know a lot about a specific thing that you can rely on, because there's a lot of details and a lot of attention you have to pay to certain things, within different steps of the process, like the printed circuit board, because this is basically the brains of it all. So got to make sure we get it right. And so when you add an A on the end of PCB, it basically just means assembly. So before the components get placed onto it, it's just a PCB, or a bare board is what we call it. And then whenever the components do get placed on top of it, it's called a PCBA, or an assembly. And so this is kind of another example of like 3D printing. Whenever we go to make prototypes, we'll, have to have all of this to be able to actually put the board in to see if it fits. And usually we don't use 3D prints to verify anything dimensionally. It's more just for general form factor, general feel, and size of different things, just to make sure everything's kind of fitting together really early on, and that there's no huge mistakes that we're really running into. And then, so for the printed circuit board, after we know exactly, the shape of it, everything that's going to go on it, the design's done, you have to do something called a panelization. So the boards obviously are in a really wonky shape. Well, some of them are. The camera boards are actually in little rectangles here on the left, so they fit really compactly, which is nice. But there's a standard board size that they use, or panel size, or panel sizes. There's multiple. But for ours, we only could fit 2 of our motherboards or main boards on one panel, and then 3, 6, 9, 12, we could fit 15 on the camera board. So that was really nice to be able to fit that many on there. But you need to have these files to basically submit to the manufacturer, so that they know how to program their machines, and the machines know how, like, where to put everything, how many are going to be there, and they can multiply, all the component counts in the computer, and make sure that everything gets situated properly. And then whenever the boards are finished getting placed onto, these are the machines that they use. So the machine on the left is a feeder. So you put the panels into the feeder, and then the feeder feeds them into this machine on the right, which this is I'm looking at it, the perspective is from behind, so this isn't the front of the line, but the machine all the way to the right is a solder paste machine. So you put the panel in that machine, and it takes solder paste, and it puts it on every little spot that it needs to be put where a component is going to go. And there's basically a silk screen like tray that is showing where all the components go. So you just have to, the machine just wipes the silk screen over it, and it has negatives for all of the holes where the solder paste needs to go. So once the solder paste is placed, it moves to the SMT machine, which is the surface mount machine. And that machine has all of our components ready on what they call reels in large quantities, stored inside of it, or right outside of it. And the machine is so sophisticated and advanced, it can, once it's programmed, it knows exactly which component to pick up from which reel, and exactly where to put it down. And it can do so at very high rates of speed. So this is a really awesome piece of equipment. And once it goes through that, it goes through an oven, which has different stages to where it kind of slowly ramps it up, slowly heats up the board and the components to where, the components just melt into the solder paste, and then it slowly brings it back down so that it hardens up. And so that's kind of how all the components get placed, is robotically. There's hundreds of components per board, and this machine basically does it all. And once it finishes, it goes through a couple of inspections. One is an automated camera, and then if it needs further inspection, it can be manually inspected, and it can also be x-rayed to ensure that there's no issues through the board or with any of the components. And there's some really cool machines that are coming out that, for example, instead of silk screening the solder paste at the beginning, now there's a dot matrix printers actually that somewhat like glop or 3D print pretty much the solder paste at specific heights for different components. And then it also inspects itself. So it'll take a picture and do an analysis and make sure that all of the glops of solder paste are the appropriate amount. And then if it has errors, it'll go back and fix itself. And there's a lot of cool things that are happening that will improve manufacturing processes and quality control over time. And so those are really exciting pieces of machinery. And I think yeah, so I have a video here. It's a very short video, but this will kind of uh, show you the capability of the surface mount machine. The picture you're seeing right here is a panel. It's only one board, one printed circuit board, but it's becoming a printed circuit board assembly because it's being placed on right now. All these cylinders that you see on this nozzle head on the left, upper left, those are all placers. So all of those cylinders are picking up parts and placing them down onto the board. So now I'll play it for you guys. So yeah, you can see, I'll play it one more time, just in case someone wants to see it again, but you can see how fast these machines place components. There are machines that I believe go above 100,000 components per hour, but I believe this machine specifically that this video is of was a machine that was doing 60 to 80,000 components per hour. Yeah, and there's also machines that do exist in other parts of the world. I believe China has a couple of SMT machines. Maybe they exist in other parts of the world as well, but I've seen one specifically in China that's like a cylindrical head that moves like this. And I think someone will have to research this and tell me if I'm wrong, but I think it was 3 to 400,000 components per hour. So it gets pretty crazy, and it'll only go up from here. You know, the technology is existing and being researched and developed and innovated upon. So I think that we're only going to get more advanced from here in terms of speed and throughput and accuracy. So really cool stuff. So yeah, whenever they get done, this is what they look like. On the bottom right, you can see it's still on the panel. So there's actually 4 boards per that panel, and they're still attached. You can see the little pieces of material still attaching them at the top and bottom. And they actually make these panels to where they have something called mouse bites where they're connected. So it makes it really easy to just tear them off. And if you needed to, you could even sand where that connection was if there was like a nub left over or something like that. But yeah, so once you depanel them, this is what they look like on the left. This is actually a foundation motherboard, so pretty exciting. And yeah, let's see what else we got here. Oh, so yeah, the camera board. Yeah, we posted this picture before, but this just goes to show you how small it can get. It can get even wickedly more small than this. But this is, the smallest board I believe that we've made. And that's it next to an Apple AirPod. So you can get the idea of just how tiny things can get. And we use these types of boards or smaller boards to attach to larger boards, or just as what we call breakout boards for specific things. So this is specifically meant for the camera, and it attaches directly to the motherboard. And then yeah, so plastics. Like I had mentioned in the industrial design process, there's also a lot of other things and manufacturing processes that happen when you're dealing with different materials. So for plastics, we prototype them with a 3D printer, with a Formlabs printer. You can also urethane cast plastics. You can CNC them if you want, but that tends to be a little bit more expensive. But with each different process, you're gaining different things, whether it be speed, accuracy, the overall quality or durability of the part. But once you finally do decide that you're going to want to make a plastic part, you have to move into making the tool for that plastic part. And as I mentioned briefly earlier, whenever you have to make, different changes to the part, you should do that before you make the tool, because once you actually make the tool and go to production, everything gets a lot more solidified, as you can see with all this big chunks of metal. So the left side is actually a tool, both halves of the tool rather, the cavity and the core. And you can see like on the right hand side of that tool on the left, it has like what the part would actually like the shape of it, and then the negative is kind of like where it fits in. So you can imagine if plastic was in between those two pieces when they were together, that's probably similar to what the plastic part is going to look like. And so on the right hand picture, you see the two halves together, and there's lots of different things coming out of it. All of those things are basically just runners or pins or gates that are helping the plastic flow more appropriately into the part, so that you get whatever shape or features that you're searching for. So this can get very intricate. I'm honestly a little bit ignorant about it and rely on a lot of other people on my team to know about it. But that's again why we have partners who know a lot about injection molding, know exactly what they're doing, and can provide us with useful information to make decisions about the direction that we want to take the project. And so that, like I had shown in the overview, there's also different sections of sampling off your tool. So you can have a T1, which is the initial parts that come off. Then you want to make changes, and then they make the changes, and then you do T2s. Well, as you go through the process, you're also finishing the tool. Basically, you can texture it different ways to make your part have different textures when it comes off, if you want it to be super shiny, or if you want it to be a matte finish, or if you want it to be glossy, or if you want it to be rough. You can have the manufacturer texture the tool differently, so that when the plastic goes through it, it creates those different cosmetic features whenever you have the finished part. And then there's also, beyond that, after the part's even finished out of the tool, you can coat the part, you can paint it, you can sandblast it, polish it, etc., to get whatever desired quality you want. So yeah, very, very complicated, but also very needed. There's a lot of demand for injection molding, a lot of demand for the people who cut the tools, who make the tools for injection molding. So it's a very interesting industry, and it's definitely going to be around for a long, long time. And so yeah, this is kind of just showing you like what the manufacturer will provide to us. This is what they call a DFM report, so design for manufacturing. Like I was talking about earlier, when you're at a prototyping stage, you can't just go, let's say you have a really nice prototype. Well, you can't just go make 1 million of those. You actually have to make sure you're designing a repeatable process, so that the parts that you're getting are all the same over and over again. So this kind of shows you like what they're planning on, where they're planning on making the parting line, which is where the two parts of the tool meet, which generally will give you some form of mark on the part. So you want to try and find a way to cover that as best as possible, whether it be with some solution with the tool, or whether it be post-processing or whatever. The selection can also make it really obvious, or make it kind of disguisable. And then this is kind of just showing you like there's a a hot runner with a pin gate going down onto this part. So that's kind of showing you like where the plastic is flowing through, and how it gets to all the other places of the part. And they also send you analyses. So the left side is a draft analysis, which is basically telling you when they separate the tool, or when they pull the part out of the tool, where is the most force or tension going to be on the part, and how do you prevent the part from breaking or scuffing or having drag marks when you pull it out or when you separate the tool. And then the thickness analysis, to ensure that as the plastic goes into the tool to create the part, you get even wall thickness across the part, to ensure that there's no mechanical points of failure, or somewhere where there's a gap where it's not going to fill with the plastic or something like that. So all of these reports really provide useful information for us to be able to say, okay, well, if this has a draft mark here, then maybe we want to change something, or maybe we're okay with having a draft mark there because no one's going to see it, or it's on the inside of the device, or there's lots of different considerations that you take from these reports, and then you revise what you need and make more parts and keep going. And then this is kind of just some pictures of like from our metal manufacturer. The leftmost picture is a robotic bending arm. So it can actually take a flat piece of metal and bend it, and then it can move different ways and bend it a second time in different orientations, and it's all automated. The middle one is a blue laser machine, and it's pretty huge. I would say it's probably, I don't know, maybe from the name, maybe it's 30 feet by 30 feet. I wouldn't be surprised if it's 30 feet by 30 feet. And so they basically just load really big sheets of metal into here, and the laser just cuts straight through the metal. I believe it can cut through pretty thick materials, maybe a 1/4 inch, maybe even an inch. I'm not sure. But yeah, it's a very capable machine and gets a lot of parts done very quickly. And then the rightmost machine is the thing that lifts the plates or the sheets of metal rather to put into the machine in the middle. So, or to put into other things, other machines. But it can lift massive sheets. It has these suction cups that lifts it up and then moves it onto rollers, so that people don't have to move these massive sheets of metal around the facility. And then beyond like the packaging and the stickers and all of the other smaller things that are involved in the manufacturing process, there's also a very important thing called regulatory testing that's required for any consumer electronic device that goes onto the market, especially if it has a processor, or especially if it's internet connected, and even more so and stringent if it's like a cellular device or something that's cellular enabled. So for our products, for hardware wallets, since it's not internet connected, we don't have to go through too many tests, but we do FCC testing, we do CE testing, self-marking, and we also do these EMC tests for safety and other things. So they do different things, but this picture is basically of an antenna that's pointed at the device that you're testing, and it sends different level frequency waves at your device to see how your device will react, and it also detects radiated emissions from your device. So they do a lot of different things. They drop a ball on the device, they try and discharge it with static electricity, they do magnetic testing with it. So there's a lot of different tests that it goes through just to ensure that it's safe, it's not going to blow up or anything like that, or cut you, or do anything crazy. And there's different qualifications for these tests, different qualifiers rather, that you use to dictate whether your device is industrial or whether it's consumer, or what specific application it's for. And then there's also country specific tests where if you're shipping to a specific country, you have to have a test, or their customs, you have to have a certification for the product if it's a certain type of product, or their customs won't let it through. So there's lots of different considerations for the testing, but it's definitely an important part of the process. And before, I was in the business of operations or manufacturing, I had no clue about any of this stuff. And it's, again, a very involved thing that, we rely on our testing facility to guide us in the right direction, give us the best advice, teach us about all of these things, and let us know what we need to do. So, yeah. And then the final part of it all is the integration. So on the very left, you kind of see like the setup of what it looks like. Each of the mats are like where somebody would stand, and it's kind of in succession of a row. So like the person leftmost would get something and they'd start it, and they'd pass to the next person who would add something else, until at the very end you have a completed either subassembly or assembly. And then you take all of your sub-assemblies and make the final product. And the middle picture is just some rear covers from our last production run. I was just showing like, this is kind of like a sub-assembly. So the little metal plate and the white part, along with the 2 foam pieces, get placed into the rear cover. And then they had to sit for the glue to dwell, and for the metal plate before they were put onto a device and packaged up into a box. So the rightmost picture is a completed passport that's been packaged up, saran wrapped, and ready to go out the door. So yeah, that's basically it. I want to just say thank you for having me. I think that manufacturing and supply chain, especially at the University of Arkansas, is an awesome choice. And if you can find a way to mix that with a passion of Web3 or crypto, that would be amazing. I hope that we see a lot more hardware devices hit the market, and we're definitely going to do our part to, continue building tools that help people reclaim their sovereignty. And we're really excited to have this mission and to be releasing these products to the public. So yeah, keep updated on our website, on our Twitter. Feel free to email me, and I will look forward to maybe seeing some of you guys, your ideas for the use cases at the kickoff. And yeah, thank you so much. Bye bye.